Welcome back, everybody. Learning is a hobby here. I wanted to uh, go back to Spivak's calculus book, since uh, if you're a regular viewer, I just finished up chapter 5 in Tao's Analysis 1 book. So we've finished constructing the natural numbers, the integers, the rationals, and finally the real numbers in Tao's book using we constructed the real numbers using Cauchy sequences. But now that we've done that, I want to return back to Spivak's book, and we'll do the construction of the real numbers in an alternate way using Dedekind cuts. So we're going to start in chapter 28, where Spivak talks about the algebraic structure of a field. So we'll take a look at my summary for his chapter 28, and then the next video will be the exercise set for chapter 28. So let's jump into it and get started on. Actually, let me move these out of the way, and we'll get started on my summary. Okay, so let me bring up my notes. Scroll up to the top. Okay, so like I said, this is chapter 28. In this chapter, the logical status of the properties P1 through P13, which have been discussed in Spivak's book in previous chapters. And again, you can see my playlist for what we've done in Spivak already on the channel. Maybe I'll post a link to that play series down below, as well as my playlist for Tao's book as well, if you want to see the construction of the real numbers done properly. So that stuff, if you want to see, you can link down below. Sorry, you can see the link down below. But so we've talked about properties P1 through P13 in Spivak's book already, but we want to scrutinize them more carefully here. All right, so the rationals, the real numbers, the natural numbers, integers have remained undefined up until this point in Spivak. Again, we constructed all those things already formally in Tau. So these can be defined carefully, and you can see like I said, my playlist down in the description bar for Tau. Okay, Spivak will assume the definition of the natural numbers, the integers, and the rationals, along with properties P1 through P12 for the rationals. A goal here will be to assume the rationals along with its properties, so P1 through P12, and use this to define the real numbers and that the real numbers satisfy P1 through P13. Right, and to do that, first we'll define what we mean by a field. So a field is a set F together with two binary operations, which we call addition and multiplication. Here we're defining an abstract field. So the notion of addition and multiplication does not necessarily mean the same operation that we mean when we talk about addition and multiplication of real numbers, for example. So these are um, abstract notions of these things. So those two binary operations are defined on F, for which the following conditions are satisfied. And there's a bunch of conditions here. So addition has to be associative. There has to be an additive identity, and there has to be additive inverses. Addition has to be commutative. Multiplication has to be associative. There has to be a multiplicative identity and multiplicative inverses for non-zero elements of the field. Multiplication has to commute. And finally, multiplication has to distribute over addition. And so three familiar examples that we know that our fields are the rationals, the real numbers, and the complex numbers. These are sets that we should be particularly familiar with the usual notions of addition and multiplication that we know of for those sets. Right, the rules 1, 3, 4, 6, 7 are just restatements of the properties P1, P4, P5, P8, P9. Again, you could see those in chapter 1, or you can watch my video for chapter 1 if you don't remember what those are. The elements that play the role of 0 and 1 are just the numbers in 0, 1 in the sets that we just talked about in the rationals, the reals, and the complex numbers, which is why we use the symbols to denote the additive and multiplicative identities. Furthermore, the number b in 2 and 5 is negative a or a to the minus 1. What that means is we use the symbol negative a to denote the additive inverse of the element a from the field. And a to the minus 1, we use that to denote the multiplicative inverse of the element in the element a in the field. For this reason, we use those symbols to denote additive and multiplicative inverse of an element, so of an arbitrary field. Some other examples of fields that are maybe less obvious than the ones that we talked about, or you may not be familiar with them, are Spivak gives 3 examples, and I prove that they're fields down below. He doesn't prove that they're fields in the book. He asks the reader to do that. So, like I said, when you get to something like that in a math textbook, you want to make sure you do that. So the first example is I'm labeling here F1. F1 is the set A plus B times square root 2, where A and B are rational numbers with the usual addition and multiplication of real numbers. So that forms a field. Like I said, I'll prove that down below in a second. The example F2 is the integers modulo 2. So it's made up of 2 equivalence classes, 0 mod 2 and 1 mod 2, where addition is addition modulo 2 and multiplication is multiplication modulo 2. All right, F3 is the set of 2 tuples A comma A, where A is a real number, where we define addition to be component-wise, and same thing for multiplication, we define it component-wise. Okay, and here's my proofs that these are fields. All right, for part A, we'll prove that F1 is a field. That's, again, just to remind you, that's this set here. All right, since F1 is a subset of R, and the addition and multiplication on F1 are the same addition and multiplication that we have on the real numbers, we automatically know that properties 1, or I guess you could call them properties, 1, 3, 4, 6, 7 are inherited from the real numbers. So we only need to check closure and property 2 and 5. Right? Closure just means that the set is closed under the operation of addition and multiplication, meaning when you add 2 elements of the set, you still get an element of the set. When you multiply 2 elements of the set, you still get an element of the set. And that's what I'm showing here. So C1, if you add 2 arbitrary elements, A plus B root 2 plus C plus D root 2, and when you simplify that, you get A plus C plus B plus C times root 2. Obviously, that's an element of F, so the set is closed under addition. All right, same thing if you multiply any 2 elements from the set, A plus B root 2 times C plus D root 2, when you multiply out, gives you AC plus 2BD plus, in parentheses, BC plus AD times root 2. Again, notice that that's an element of the set F1. So that means that the set is closed under addition and multiplication. Okay, and then we show that there is an additive identity and that there are additive inverses, which I'm showing here. A plus B times square root 2 plus the element 0 plus 0 root 2 is equal to A plus 0 plus B plus 0 times root 2, which is A plus B root 2. So that shows that 0 plus 0 root 2 is an additive identity. And then finally, if you add A plus B root 2 to minus A minus B root 2, that gives you A minus A plus B minus B root 2, which is 0 plus 0 root 2, which is the additive identity. Therefore, additive inverses exist. Right, and then similar thing for multiplication. So this is property number 5. 1 plus 0 root 2 acts like the multiplicative identity, which I'm showing here, just using the rule for multiplication. And then we want to show that there are, for non-zero elements, there are multiplicative identities. Sorry, inverses. So here, if A plus B root 2 is not 0, then obviously A and B are not 0 because the additive identity is 0 plus 0 root 2. If I multiply that by this element here, that I notice this, first of all, this element is an element of F1 because ratios of rational numbers are rational. So this, the first component and the second component that's multiplying root 2 are both rational. And if I multiply these together and simplify, you get the multiplicative identity. Right, so you can see that worked out here. Note that A squared minus 2B squared is not the additive identity, since a squared minus 2b squared equaling 0 would imply that 2 is the square of a rational number. But again, we know that square root of 2 is not rational. So we don't have to worry about, this number not being well defined. So multiplicative identities exist. All right, and that shows that F1 is a field. All right, then we can show F2 is a field here. F2 is the integers modulo 2. That's this set here. So we can prove all the rules using the addition modulo 2 and the multiplication modulo 2, the tables that I have here. And this is a finite field, and there's only two elements, so all you have to do is just check literally all the cases. So that's what I did here. So I checked property 1 for all of the possible cases that you can have. There's 8 of them. So that checks out. Checked all the cases for 2, and so I won't, bore you with the details, but you can pause your screen if you want to see the proof here. So all of the properties are satisfied by F2, therefore it's a field. Okay, and then just for a change of pace, I proved that F3 is a field using a different kind of proof that is not in the spirit of Spivak's book. I just wanted to mix things up a bit because doing, just showing that the I don't want to say axioms, the properties that we listed 1 through 7 for a field um, are satisfied is kind of boring. That's the way you should do it. So just do what I say, not what I do. But I just wanted to show you a different kind of proof here. So here I used more of an algebra proof that you see in like an algebra book or something. So to prove that F3 is a field, I defined a function f from the real numbers to the set A, where A is the set of all um, two tuples A comma A, where A is an R, and the function is defined at the input x as has the output x comma x for all real numbers x. Right. So first thing, if x and x prime are real numbers such that f of x equals f of x prime, then x comma x equals x prime comma x prime. And by the way, we defined equality of ordered pairs. That means that x is x prime. So what does that mean? That means that f is 1 to 1, or if you want the fancy term, it's injective. Right. Next, let x comma x be an arbitrary element of the set A. Then f of x is equal to x comma x, since x is a real number. That implies that range f is equal to the set A. Therefore, that means that f is onto, or again, if you want the fancy word, f is surjective. And those two things taken together show that f is a bijection. It's bijective. Right. Then we can take two arbitrary elements in R. And if we look at f of x plus y, by the way, we defined the function, that's x plus y comma x plus y. But by the way, we defined addition on this set, that's the same thing as x comma x plus y comma y, which if you notice is f of x plus f of y. And similar thing happens for f of x times y, right? F of x times y is the ordered pair xy comma xy, which is equal to x comma x times y comma y. By the way, we defined multiplication on the set, which if you notice is f of x times f of y, right? And those two things show that the function f is a ring homomorphism. Since f is a bijective ring homomorphism, it's a ring isomorphism, and therefore all the algebraic of properties um, that R possesses are transferred over to the set A. Therefore, A is also a field. Okay, here's a note. Fields provide an ideal framework in which to discuss the properties of numbers in the most economical way, since P1 through P9 hold in any field. Right? Some properties of the fields Q, R, and C do not hold in all fields. And then just as an example, in F2, 1 plus 1 is 0. Consequently, 0 minus 1 equals, that's equal to 1, because minus 1 is equal to 1 in this field, right? But that's the same thing as 1 minus 0. But notice that 0 is not 1. So that's not a property that exists in Q, R, or C. Right? Then we want to move on to the order relation defined on um, certain fields. So an ordered field is a field F. This is the abstract definition of an ordered field. An ordered field is a field F together with a certain subset P of F with the following properties, right? Property 8, for all A and F, one and only one of the following is true. A is equal to 0, A is in the set P, or negative A is in the set P. And this gives you trichotomy. Um, Number 9, if A, B are elements of P, then A plus B is an element of P. And property 10, if A, B are elements of P, then A times B is an element of P. Okay, and just as a note, the rationals, the reals, F1 and F2 are ordered fields, but the complex numbers C and F2 are not. And I didn't prove those statements, but I just gave a sketch just because I didn't feel like writing uh, things out like in because it would take even more even more pages to do that. So I just showed you what the set P is, and you could verify yourself if you like that um the set works. So, for example, for Q, the set of positive numbers is the set of all Q and Q, where Q is greater than 0. It's easy to check that that works. For R, again, it's the set of all real numbers greater than 0. For F, the positive numbers are A plus the set of all A plus B square root 2 and F1, where A and B are positive. For F3, the set of positive numbers is all A comma A in F3, where A is greater than 0. And then for part 5, the fact that C cannot be made into an ordered field is Spivak says in the appendix, or the in the epilogue, um, that the fact that C cannot be made into an ordered field is addressed in an earlier chapter, which we haven't reached in the video series yet, but we will eventually. Okay, and then finally, part 6, F2 is not an ordered field. Since 1 equals -1 in that field, that implies 1 is an element of P by part 8, by property 8, and 1 plus 1 equals 0 would imply that 0 is an element of P, which that's implied by part 9, or property 9. However, 0 is an element of P contradicts part 8. So F2 cannot be made into an ordered field. Okay, another note, if it is natural to introduce notation for an arbitrary ordered field, which corresponds to that used for the rationals and the reals. So here, we're just defining what we mean by these order relations. A greater than B if A minus B is an element of P, A less than B if B greater than A, and et cetera, et cetera. Okay, for an arbitrary ordered field F, these definitions can be made for an arbitrary field. A set A of elements of F is bounded above if there's some X in F, such that X greater than or equal to A for all A in the set A. Any such X is called an upper bound for A. If an element X of F is, an element X of F is a least upper bound for A, if X is an upper bound for A, and X less than or equal to Y for every Y in F, which is an upper bound for A. Right, then we have a definition of what we mean by a complete ordered field. A complete ordered field is an ordered field in which every non-empty set which is bounded above has a least upper bound. And now there are two questions that will be answered in the following two chapters, which make up the remainder of the epilogue, where we'll be constructing the real numbers. The first question is there a complete ordered field? We're going to prove that in the next chapter. And then is there only one complete ordered field? We'll prove that in the chapter after the next. All right, our starting point will be the rationals assumed to be an ordered field, having the additional property, which we call the Archimedean property. So I'm stating it here, so just to remind you of what that says. Let X be an element of the rationals with X greater than 0. Then for any Y in the rationals, there's some N in the natural numbers such that NX is greater than Y. Okay, and then just a final note here. The Archimedean property does not follow from the other properties of an ordered field. When Q is constructed, again, you can see my videos that I made in my playlist for Tao's book, where we actually did this. So we constructed N, Z, Q, and R in those videos. When Q is constructed, properties P1 through P12 appear as theorems, and so does the Archimedean property of Q. Right. And that's the end of my summary for section 20 or chapter 28. The next video, let me just stop my screen share, will be the solutions to the exercise set for this chapter, which is I don't want to say it's long, but there's a few there's definitely a few problems there to tackle. Let me just see number how many problems there are. It looks like there's 11 and some of them have multiple parts. But the next video will be my solutions for that. And to end the video, I just wanted to uh, read a quote from Jonathan Swift that Spivak includes at the beginning of each of his sections of the book. Not the specific quote. I mean, at the beginning of each of the sections of the book, he has a quote from someone that pertains to the material that's coming up. So the quote by Jonathan Swift here says, "This was a most ingenious architect who had." Sorry, my eyesight is not so great. This was a most ingenious architect who had contrived a new method for building houses by beginning at the roof and working downwards toward the foundation. So that's the quote for part 5, which is the epilogue. Which is the epilogue. That's what we're doing now. So again, just to remind people, if you are not familiar with the series here for Spivak, I started at the beginning of Spivak a while back and went up to chapter 8. Then after I finished chapter 8, we turned to Tao's book to construct the real numbers in a certain way. Now we're going to go to the epilogue of Spivak's book, construct the real numbers a different way. And then I'm going to continue with Spivak starting at chapter 9 where we left off. And then we'll finish Spivak's book. And then once we do that, we'll finish Tao's book. So both of these books will get finished, hopefully sometime this year. So thanks for watching. If you stayed this long, give me a like and subscribe and let me know what you think down below. And I'll see you guys in the next video.